All right, so now let's do some examples of this. Let's look at number 2 here. And it says use the given graph of f to find a number delta such that, okay, so what they're doing is they're giving us a graph. Okay, so here's f of x. And they're saying, now if you notice, f of x moves along, but there's an open dot here, and it's defined up here instead at the number 3. This is typical of you understanding, of helping you understand that the limit doesn't care what's going on at the actual number 3. It just cares about what's going on around it. And the reason for this is the fact that when we're looking for the slope formula, for the slope, sorry, of a line that's tangent to a curve, okay, we are concerned with Q values going to P values. And as Q gets closer to P, the X values on the bottom, remember we have X2 minus X1 underneath Y2 minus Y1. The X2 value gets closer and closer to X1 value, and eventually it goes off to 0. Well, if Q is on top of P, all right, then it equals 0, and that's not good. So this is a limiting process. There's a limit to how close Q can get to P. It cannot be on top of P. And that's why over here with the graph, we don't care what's going on at 3 exactly. We don't care that the function jumps some. Okay, we're only concerned with what's going on around it because these Q's are getting closer to P, but not actually getting to P. So we don't really care what's happening at P itself, just around P. All right, so let me erase all of that. Get rid of it, delete. Okay, so with this problem here, we're having to find out what the number delta needs to be for f of x minus 2 to be less than 0.5. So we're going to have to pick the minimum delta, basically. So we have to find the minimum delta that works for both sides. Well, it seems to be, well, this is 0.8 over here, and in between here, this is 0.4. So it looks like delta has to equal to be 0.4. There you have it. So let's see, using it to find a number delta. Yeah, that's it. So the delta has to be 0.4. All right, now let's look at another one. This is a little different. Find a number delta such that if, so now we need to find the delta that works on both sides, okay? So that whenever you pick an x value in between the vertical lines, these vertical lines, when you pick an x value in between these vertical lines, it lands in between the horizontal lines, okay? All right, well, let's just see. It looks like our function is y equal x squared. So let's take y equal x squared. So x squared is equal to 0.5 on the bottom. So this is the lower one. So let me call that h1. So for h1, we have x squared equals 0.5. So x equals 0.707. 1. Okay. This is now for h2. All right. So this was h1. So for h2, x squared is equal to 1.5. And then we get x equal to 1.224. All right, so essentially what that means is that here, this is 1.224, and here on the left of 1, this is 0.7071. Okay, so what is the smaller of the two from 1? So 1 minus 0.7071 is equal to 0.2929. And then 1.224 minus 1 is 0.224. So the lesser of these two is 0.224. This is less. This is the lesser of them. So we set delta equal to 0.224. So let's write this out using the definition of limit. Okay. So it says basically the limit. Let's see, it's x squared, and we're going closer and closer to 1, and 1 is the limit. So basically, it says if we choose epsilon to be equal to 0.5. Epsilon's here and epsilon's here, and the difference here is 0.5 and 0.5. Okay, we choose epsilon to be 0.5, then delta must equal 0.224 so that any x between, let's say 1.224 and what is 1 minus 0.224, 0.776, so that for any x between those two, f of x is between 0.5 and 1.5. Okay, so going up to the graph, let me erase some of this. So we choose our epsilon to be 0.5. Epsilon equals 0.5. Now, this is 0.224 one out. So this side, the one on the right, one out. So I'm going to have to redraw a new one over here so that these two values are equal. This is both delta. Delta equals 0.224. So on the right, this is 1.224. And on the left, this is, what do we say it was? 0.776. So what's happening here is if we choose an x in either one of these, f of x lands between them. If we had picked the larger of the two, this 0.229, to be the equidistance away, okay, then x wouldn't have landed in that region, okay? All right, so you can do the same thing with the previous example as well, all right? Now, there's cool stuff in the book that you really should take advantage of, okay? So in the Stewart book, they give you these really neat functions. You pick a function, so this is e to the x, all right? And you pick an epsilon value, so you pick your h's, okay? And your this right here gives your point. Your point can be anywhere, right? Give your point. Now, if you start with delta, okay, you choose a delta. Once it turns red, that tells you that an x value will fall outside of the L range over here. Okay, so for example, if we play around with this a bit, okay, so suppose you choose your delta way too big, then what's going to happen here is, oops, if you pick, so epsilon, here's epsilon, mind in its own business. Let me pick, here's epsilon, okay, it's this distance. If you pick your delta way too big, then you can pick an x in here. Let's pick this x here. And you go up, okay, everything's fine, it's still going to land in the right, in the correct area. But if you pick an x over here, it's a little further away, then it's not going to land in there, okay? So what this says is this delta is too big. It's too big. All right. All right. So you can do this for a lot of different functions, actually. There's another one here, 1 over x squared plus 1. You pick an epsilon value, and then you see what delta values work. So sometimes they're really small, okay? So it depends on where you're at on the graph, though. Okay, see how narrow the delta values are. If you pick a value where the graph is not so steep, then your delta can be a little bigger for the same exact epsilon, okay? All right, there's another one I want to show you, which is kind of cool. There's a different one in the book. These are the media parts of the book, okay? Where it's the same idea, okay? You move stuff around at all. All right, and this actually will test you. You can go through and test yourself on this. All right, and then there's another one as well. And so the book actually gives you some great examples. All right, so look in the media part of the book. So find these in the media. So now what I want to do is I want to do an example using the definition directly. Okay, and I want you to not memorize how to do these. I want you to know how to do these. Okay, so let's go through the definition first. So it says for every epsilon greater than 0, there is a corresponding delta greater than 0, such that if 0 is less than absolute value of x minus a is less than delta, then absolute value of f of x minus L is less than epsilon. Okay, so this means if this is true, if the limit as x goes to a of f of x equals L, then this is true. Okay, so let's do a problem where we prove one of these limits. So let's prove the limit as x goes to 3 of 2x plus 1 is equal to 7. So if you plug 3 into x, you get 6 plus 1 is equal to 7. So it's definitely true. We're just proving it's true. Okay, so here's the preliminary step. Okay, and this is going off of the definition. So let's keep the definition in mind. Okay, so the preliminary step is we must, given an epsilon greater than 0, we must find a corresponding delta greater than 0 such that if 0 is less than x minus a and absolute value is less than delta, then absolute value of f of x minus L is less than epsilon. Okay, so how do you go about this? Well, if we start out with this last piece here, okay, and play around with it a bit. So in this case, f of x is the 2x plus 1, and the L is 7. So 2x plus 1 minus 7 has to be less than epsilon. Okay, this is that f of x minus L piece. All right, so now let's manipulate this. This is 2x minus 6 is less than epsilon. Take out a 2. This is x minus 3 is less than epsilon over 2. Oh wait, well, epsilon, and now divide by 2. X minus 3 is less than epsilon over 2. Now, this x minus 3 is this piece right here. okay? Because A in this case is 3. This is A, all right? So we have already that absolute x minus 3 is less than epsilon over 2. So if we choose delta to equal epsilon over 2, then we're done. It's less than or equal to epsilon over 2. So here's the proof. Let me show you. Proof. Given epsilon greater than 0, choose delta to equal epsilon over 2. Then, and now we just go backwards. All right. Then 0 is less than x minus 3 is less than delta. Implies then that absolute value of x minus 3 is less than epsilon over 2, which implies then that 2x minus 3 absolute value is less than epsilon, which you can pull the 2 in. 2x minus 6 is an epsilon. And now we can make it 2x minus 1 plus 7. Wait, is that what we want? No, plus 1 minus 7. Plus 1 minus 7 is less than epsilon. And we're done. We got it. So we prove it. So done. All right. So that's how you do it. You need, if you were going to do this on a test, I would want the blue piece here. I would want all this red piece here. And I would want all this green piece here. Okay. So since I want you to know how to do this on a test, let's try another one. All right. So prove that limit as x goes to, let's say, -4 of 2x plus 5 is equal to, this is -8 plus 5 is -3. Okay, so first step is preliminary step. So preliminary step says we given an epsilon greater than 0. Where I'm getting this all is from the definition. It says, using the definition, it says for every epsilon greater than 0, there's a corresponding delta greater than 0, ... So I'm saying, given an epsilon greater than 0, we must find a corresponding delta greater than 0. That's where I'm going next. Okay, we must find a delta greater than 0 such that if, and I'm going to put in the actual values now, x minus or minus 4 is less than delta, then absolute value of 2x plus 5 minus or minus 3 is less than epsilon. So let's clean this up. So it says if 0 is less than x plus 4 is less than delta, then 2x plus 8 is less than epsilon. Okay, so we don't need any of this, really. Done with that. All right, so the thing you do is you play around, you manipulate mathematically that last piece. So we start out with, well, let me do this in red. Say, okay, well, 2x plus 8 is less than epsilon. Now I want to make it look like x plus 4. Okay, this is my goal. We'll just take out the 2. X plus 4 less than epsilon. And now I'll divide by 2 less than epsilon over 2. And now make it look like the other one. X minus minus 4 is less than epsilon over 2. X minus minus 4 is here. Okay, so we're going to choose delta to equal epsilon over 2. And so the proof, I did this in green, the proof is this. Given epsilon greater than 0, choose delta to equal epsilon over 2. Then 0 less than absolute value of x minus 4 less than delta implies then that absolute value of x plus 4 is less than epsilon over 2, which implies then that 2 absolute value of x plus 4 is less than epsilon, which implies then that absolute value of 2x plus 8 is less than epsilon. Now, what was the original? 2x plus 5 minus 3 minus 3. So this implies then that 2x plus 5 minus the negative 3 is less than epsilon, and then we're done. That's it. Okay. So what I want you to do is I want you to see notes for a quadratic example. Okay. And see media in book. Okay, let me see if I can find it. So here's an example of where you're dealing with a quadratic. Okay, and this is there's a level of difficulty that pops up in here, and so this is how it's done. Okay, if you're interested, I may give a bonus on a test if you can do this. Okay, so that's an example of one of those. Let's move on to something else. So now what I want to cover is infinite limits, and this will just be the last thing, okay? So take a second to read this, so stop the video and read this definition, and I'll explain it to you. So what this is basically what's happening here is we have a graph that is going off to infinity, okay? And as it's going off to infinity, all right? And so as x gets closer and closer to a, the graph goes off to infinity. So there is no limit, okay? So there's no limit here, all right? Or actually, the limit is infinity, okay? No, it's kind of the same thing. It's just saying it two different ways. So what do you do? Well, the way you do this is the following. You say, the way you prove it, or you make the definition really precise, is you say, okay, let me draw this out. Okay, so we have a function, and let's draw the function in blue. And suppose you're getting closer and closer to a on the x-axis. This is a, and so there's an s. Okay, so now what's happening here is that the limit is infinity if you can choose an m, okay? Someone hands you an m, all right? And there's a corresponding, let's use purple, there's a corresponding delta. So delta's here, such that if x is between the two delta values, okay, if x is between, this is a minus delta and a plus delta, x is between those, f of x is going to land above m. All right. So this time you don't want f of x to be bound at all because the limit is infinity. Okay, limit's infinity. So that's the basic idea. So let's do this example here. I'll show you. So it says prove, an example, prove that limit as x goes to 0, which 0? Okay, not from the right or left, just 0, of 1 over x squared is equal to infinity, okay? So given m greater than 0, we must find a delta greater than 0 such that if 0 is less than x minus a is less than delta, f of x is greater than m. So let's write out what we have here for this function. What we have is 0 is less than absolute value x minus 0 is less than delta. The a in this case is 0, right? F of x is 1 over, oh wait, this needs to be greater than m. Greater than m. This is 1 over x squared is greater than m. Okay, let me clarify this for you. So the deal is we're looking at 1 over x squared, which looks like this. Okay, and we're determining that as you go into 0, okay, as x is marching towards 0, the limit is infinity. Okay, so this is going off to infinity. So what we're doing is we're choosing an m. Well, we're given an m, and then there's a corresponding delta such that if x is inside of that delta, okay, then f of x, okay, f of x is greater than m. So here's f of x. This is f of x. And f of x is certainly greater than m. Okay, so that's why it's got to be greater than. All right, so that's what we have. So this piece here is that. So as usual, we play around, we manipulate the f of x part. So I'm going to take that over, and I have 1 over x squared greater than m, which implies then that 1 is greater than mx squared. Multiplying both sides by x squared. X squared is positive, so it doesn't flip the negative sign. It doesn't split the inequality sign. M is positive, so I can divide by it without any problems. So we have x squared is less than 1 over m. Now I'm going to take the square root of both sides. Square root is an increasing function, so it's an increasing function. Any increasing function will not affect your taking the root of both sides. Okay, if a function's increasing or it's completely decreasing, you can apply it to both sides of an equation of an inequality, and the inequality sign will not change. So since square root is an increasing function, it never decreases also, then when I take the square root of both sides of this equation, the inequality sign is not affected. Okay, so we're at this point. So, well, that's what we needed here, because this absolute value of x is less than delta. By the way, when you take the square root of x squared, it's the absolute value of x. So ask me about this if you need to. Anyway, so what I'm going to do, I have absolute value of x by itself. Here's absolute value of x by itself. So I'm going to choose delta to be equal to square root of 1 over m. Okay, so now here's the proof. So let me do the proof in green as before. Proof of limit as x goes to 0 of 1 over x squared is equal to infinity. Okay, so choose given any m greater than 0, choose delta to be equal to square root of 1 over m. It's from here. Then we see up here that delta is equal to square root of 1 over m. Then that means that absolute value of x is less than 1 over m. So absolute value of x is less than square root of 1 over m. Now we're going to square both sides. So we get x squared less than 1 over m, which implies that x squared m is less than 1, which implies then that m is less than 1 over x squared, which is what we wanted. Yeah, we wanted 1 over x squared is greater than m, which is what we wanted. See, that's up here. And so that's the proof. There we go. So these problems weren't too bad necessarily if you understand the material. Try to understand them though. They're actually kind of interesting. And this is the basis, all this is the basis for all calculus. So the more you know epsilon delta proofs, the more you're really going to know the theory of calculus. And you're going to be a better student too.